Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, what is the number of moles of 30.75 grams of C2H6O? Okay, so the first part in answering this question is we need to find the molar mass of our compound. Okay, so finding the molar mass is pretty easy. All we need to do is look at the periodic table, find out which atoms make up our compound, and then multiply them by however many atoms are in that compound. So for example, the molar mass of carbon would be multiplied by 2, and then we would add 6 times the molar mass of hydrogen plus the molar mass of oxygen. So again, these values are just found on your periodic table. Carbon's molar mass is 12.01 grams per mole. And in the case of hydrogen, it's 1.01 grams per mole. And for oxygen, it's 15.99 grams per mole. Okay, so now when we add all these values up, we get the final molar mass of this compound, which is 46.05 grams per mole. Okay, so that was step 1 of answering this question. The second part is just calculating now for number of moles. So the formula for finding number of moles when you're given mass and molar mass is just dividing mass over your molar mass. So the mass was given in the question. It was 30.75 grams. And the molar mass is what we just found in the previous step, 46.05 grams per mole. So now if we divide this, our grams will cancel out, and our moles will now be our main units, and you end up getting 0.668 moles. And that is our final answer. Okay, so now let's see what the junior tutor said. To obtain the number of moles of 30.75 grams of dimethyl ether, or C2H6O, we need to obtain its molar mass first using the atomic masses of its components. So they showed all the different steps when they multiplied out the molar mass of carbon, hydrogen, and oxygen. And when they added it up, they got 46.048 grams per mole. Now we simply divide the given mass of dimethyl ether to its molar mass to obtain its number of moles, and they also got around 0.6678 moles. So this solution is correct. Okay, so question number 2. For this amino acid sequence, so we have glu, met, arg, dr, and gly. So these are all the 3 letter symbols for these different amino acids, and they want us to write the sequence using the one letter symbol. So before we write out the one letter symbols, let's first try to identify each of these amino acids based on their three-letter symbols. So for example, GLU is glutamic acid. MET is methionine. ARG is arginine. And this THR is threonine. And finally, GLY is just glycine. So now that we have identified each of these amino acids, we can write out all of their one-letter symbols. So in the case of glutamic acid, its one-letter symbol is E. Methionines is pretty easy, it's just M. Arginines is an R. Threonines is a T. And glycine is G. And now we can write out the sequence of these one-letter symbols. So it's going to be E, M, R, T, G. And the junior tutor said that the one-letter symbol for glutamic acid, methionine, arginine, threonine, and glycine are E, M, R, T, and G. Therefore, the one-letter symbol for the sequence is EMRTG. Yep, so this solution is correct. Okay, so question number 3. If 11 grams of aluminum and 29.6 grams of copper 2 oxide are mixed, what is the theoretical yield in grams of aluminum oxide which could be produced? Okay, so before we try to answer this question, we have to first write out a balanced chemical equation for this reaction. So we have aluminum, I guess is a solid, plus copper 2 oxide. So copper has the oxidation number of 2, so only one oxygen is needed since oxygen also has an oxidation number of -2. So it's just going to be CO. Maybe this is in its aqueous form. And a single displacement reaction would occur with these compounds. So basically, now we have copper solid, and aluminum is now with the oxygen. So aluminum's oxidation number is 3+, and oxygen's is 2-. So our formula is Al2O3. And now we need to balance this equation. So we have 2 aluminums on our product side and only 1 on our reactant. So I'm just going to put a coefficient of 2 in front of that aluminum. And we have 3 oxygens on our product side. So again, I'm just going to put a 3 in front of copper 2 oxide. And now we have 3 coppers on our reactant side. So I just need to put a 3 in front of the copper on our product side. So now everything should be balanced, and under each of these compounds, I'm just going to write out everything we know. So we know the mass of aluminum is 11 grams. And we can also write down the molar mass of aluminum, which can just be found on your periodic table. It's 26.98 grams per mole. Okay, so these are all the variables we know for aluminum. So now let's do the same thing for copper. We know the mass of copper 2 oxide is 29.6 grams. And we can calculate the molar mass of copper 2 oxide just again by going on the periodic table, finding the molar masses of both copper and oxygen, and when you add them all up, you should get a total molar mass of 79.55 grams per mole. And in the question, we want to find the theoretical yield in grams of aluminum oxide which could be produced. So under aluminum oxide, I'm just going to put that our mass is unknown. And I can also write out the molar mass of aluminum oxide as well. So 2 times the molar mass of aluminum plus 3 times the molar mass of oxygen gives us 101.96 grams per mole. Okay, so I wrote out everything that was given. Now I can try to start answering the question. So step 1 is to find the number of moles of both of our reactants. So the equation for number of moles is equal to mass over molar mass. So let's do aluminum first. Its mass was 11 grams, and its molar mass is 26.98 grams per mole. So we get a final number of moles equal to 0.408 moles. Now let's find the number of moles of copper 2 oxide. Its mass is 29.6 grams, and its molar mass is 79.55 grams per mole. So if we divide this out, you end up getting 0.372 moles. Okay, so step 2 is to now find the theoretical number of moles of aluminum oxide. So to do that, we need to use molar ratios to go from one number of moles to one of our products. So for example, we know that 0.408 moles of aluminum is in our mixture. And if this was to react and completely, then we know from our balanced equation that 1 mole of aluminum oxide is formed for every 2 moles of aluminum. And that's how you convert from moles of aluminum to aluminum oxide. So it's pretty much dividing its number of moles by 2. So you get 0.204 moles of aluminum oxide if all of our aluminum reacts. And now let's do the same thing for the copper 2 oxide. So there are 0.372 moles of copper 2 oxide, and we know that 1 mole of aluminum oxide is produced for every 3 moles of copper 2 oxide. So now we have 0.124 moles of aluminum oxide formed if all of the copper oxide reacts. So now we need to compare the two and figure out which one is the limiting reagent. In this case, it is the copper, since it has a smaller value of aluminum oxide being formed. So therefore, the limiting reagent is the copper 2 oxide. And we also know that this is the maximum amount of product we could form from this reaction. Because once the copper 2 oxide runs out, then we're not going to form any more product. So now step 3 is to now find the mass. So for this part, we use the equation mass is equal to number of moles times the molar mass. So we know the number of moles is going to be equal to the 0.124. And we found that out from the previous step. And I also have the molar mass of aluminum oxide, which is 101.96 grams per mole. So that's why when it comes to these kinds of questions, I like to write down what is given. It just makes it easier to do all the calculations in the end. And now when we multiply this out, you should end up with around 12.64 grams. Okay, so now let's see what the junior tutor said. In order to solve the problem above, we first write the balanced chemical equation for the reaction of aluminum and copper 2 oxide. Okay, so they wrote out the same balanced equation, and then after writing the balanced equation, we will focus on the given data. So they wrote down everything they knew, and now we will convert all the given information into moles. Number of moles of aluminum was 0.408, and for copper 2 oxide it was 0.372. And now if all of the aluminum were to be used up, so then they found out, this is a different way of finding out whether or not which one is the limiting reactant. So they found out that you needed 0.61 moles of copper oxide to react with all of the aluminum. And when they compared it to how much they actually had, we have less moles than what's needed. And now they just found the mass. Okay. And they got 12.64. Let me just double check my answer. Yep, so they got the same thing. So this solution is correct. Yep, so this is a different approach on how to answer the question. Now on to question number 4. A 50.0 gram piece of metal at 305 degrees Celsius is dropped into 610 grams of water at 26 degrees Celsius. The water temperature rises to 28 degrees Celsius. What is the specific heat of the metal? So to answer this question, we're going to be using the following equation where Q is equal to mc delta T. So let me define what each variable means. Q is like the heat of the reaction, and it can be in joules or kilojoules, depending what is given in the question. M is the mass of whatever component you're focusing on, and it's given in grams. C is the specific heat capacity. And depending on the type of compound you have, it'll have a specific value. And its units are in joules divided by grams times degrees Celsius. And finally, delta T is the change in temperature. So it is T final minus T initial. Okay, so notice that they give us two different masses. We have the mass of our metal and also the mass of our water. And we also have the initial temperatures of both the metal and the water. So the metal was 305 degrees Celsius and the water was 26 degrees Celsius. And then after the metal was added, the water temperature changed to 28 degrees Celsius. So for part 1 of answering this question, we are first going to solve for Q that is gained by the water. And the reason why we're going to do water first is because the specific heat capacity of water is a known value. So I'm just going to write it up here. And its value is, oh, it's cut out. So the specific heat capacity of water is 4.184 joules over gram times degrees Celsius. Okay, so this value is known. And that's why we can just use our equation to solve for the Q, or the amount of heat that was gained by the water. So the mass of water was 610 grams. The specific heat capacity is 4.184 joules over gram degrees Celsius. And finally, when we look at delta T, the final temperature of water was 28 degrees Celsius, and initially the water was 26 degrees Celsius. So now if we multiply these values out, you end up getting a Q of 5,104.48 joules. So this is the amount of heat that was gained by the water. And now let's recall that heat is lost by the metal. Because some of the metal's heat was transferred to the water, that means heat was lost by the metal. So therefore, its Q value will be negative. So when we move on to step 2, which is finding the specific heat of the metal, it's going to have the same value of heat that was lost by the water, or that was gained by the water, except this time its value is going to be negative. So Q is equal to negative 5,104.48 joules. And now we can just plug in all of our variables for the metal this time. So the mass of the metal was 50 grams. And we're trying to solve for the C. So C of metal is unknown. And finally, for its temperature difference, we have the final temperature as 28 degrees, and the metal's initial temperature was 305 degrees Celsius. So now let's try to solve for our unknown. If we divided 5,104.48 by 50, and then by 28 minus 305, we get a specific heat capacity of the metal equal to 0.369 joules over grams degrees Celsius. Okay, so now let's see what the junior tutor said. In order to solve for the specific heat of the metal, the first thing that we need to know is that the quantity of heat gained by the water is equal to the quantity of heat lost by the metal. This heat gained by the water is calculated using the following equation. Q equals MC initial final temperature minus initial temperature. And then they just defined all of the different variables. From the given above, we can solve for the heat gained by water, and they also got 5,104.48 joules. So since this is gained by the water, therefore this is also the quantity of heat lost by the metal, and it's going to be a negative value. So using the same equation from above, we will now compute for the specific heat of the metal, and they also got 0.369 joules over grams degrees Celsius. So the solution is correct. Okay, so question number 5. Glucose and other dietary monosaccharides like fructose and galactose are very soluble in water at a neutral pH. For example, over 150 grams of glucose can be dissolved in 100 milliliters of water at 25 degrees Celsius. What features of the chemical structure of glucose makes it so soluble in water? Okay, so first let's draw the structure of glucose. It's like a 5-membered carbon ring. And I'll draw all of the different side groups on glucose. We have another carbon alcohol group. And then attached to each of these carbons is an OH group. So they have different orientations. But this is the structure of glucose. So if we look at glucose, we can see that it contains a lot of polar carbon-oxygen and oxygen-hydrogen bonds. So therefore, this dissolves in water. And it also helps to remember the phrase that like dissolves like. So meaning polar substances will dissolve other polar substances. So if we were to draw the structure of water, which is H2O, you'll get something like this. So it has a bent configuration, and also oxygen is much more electronegative than our two hydrogens. So there's going to be an overall dipole moment going towards the direction of the oxygen, and this leaves the water molecule having a partially negative side and partially positive sides. So this is what makes water polar. And since glucose also contains a lot of these polar bonds, therefore it can dissolve in water. So now let's see what the junior tutor said. One of the basic principles of solubility is that like dissolves like. Water is a polar solvent consisting of hydrogen bonds, so H oxygen bonds. And if an added solute is polar and can disrupt and form new hydrogen bonding with the water molecules, the added solute can be considered soluble. Now consider the structure of glucose, fructose, and galactose shown below. So here they have the linear structures of all of these different sugars, and they highlighted all of the alcohol groups that are contained in the structures. So monosaccharides like glucose, fructose, and galactose all have several hydroxyl groups in their structure. These polyhydroxy groups can interact with the hydrogen bonding present in water, and aside from that, it makes the molecule slightly polar. Because of like dissolves like, monosaccharides like glucose become soluble in water because of their polyhydroxy groups. Yep, so this solution is correct. Okay, so question number 6 is to study the following polypeptide chain written below A, draw the structure of the polypeptide as it would appear if placed in a solution whose pH is 1. Show the structure and calculate its net charge at pH 12. And finally, define the isoelectric point of an amino acid. State its importance in protein chemistry. So first, let's look at the polypeptide chain that we have. And this is the 3-letter symbols for all of these amino acids. And let's just define what each of these amino acids are. So when we have TYR, this is the tyrosine amino acid. Gly is glycine. That Liz is lysine. And finally, the glue is glutamic acid. I'm gonna run out of space, so let me just move that over. Glutamic acid. Okay, so now that I have defined what each of these are, I'm first going to draw out all of the different amino acids bonded together. And then I'm just going to label what all of their pKa values are, or I try to answer the question. So every amino acid has an amine group. And what makes each of these acids unique is that they have a different R group. So first I'll draw the R group for tyrosine. So tyrosine has this phenyl ring and also an alcohol group attached to it as well. And then I'll just draw the rest of the amino acid. So I'll draw its carboxylic acid functionality. And then I'll just start to draw the next amino acid, which is glycine. So here is glycine's amino group. And glycine is one of the more simpler amino acids, so its R group is only a hydrogen. And then this is its carboxyl functionality. And now we'll start to draw lysine. So this is the amino group on lysine. And now if we were to draw its R group, I'm just going to draw its chain. I think it has a 4-carbon chain. With an amine group at the end. And then I'll draw the carboxylic functionality of the lysine. And then finally, we'll draw glutamic acid. So this is its amine group, its carbon, and then it has a 3-carbon chain. And the reason why it's glutamic acid is because it contains a carboxylic acid at the end, like so. And I'll also draw out the end of the polypeptide chain, which is its carboxylic acid group, like that. Okay, so now that we have the structure written out, we're going to look up the different pKa values of these amino acids. Okay, so here's a nice chart that summarizes all the different pKa values of these different amino acids. And notice that they have it for all of their carboxy groups, all of their amino groups, and also for all of the side chains. So let's look at tyrosine first. So its pKa group for the amino is 9.11. So let me just highlight this in green and then show that its pKa is 9.11. And we don't have to worry about its alpha carboxy group because it is part of the chain, so it doesn't have a hydrogen there. But we also want to look at its side chain. So the side chain, which is the alcohol group on the phenyl ring, has a pKa of 10.07. I'm also going to circle this and say the pKa is 10.07. Okay, so now that was all of the tyrosine. So notice that for glycine, you can't deprotonate its side chain, so we don't need to write anything down for glycine. And now let's look at lysine. So it's found here under the basic amino acids, and I'll highlight this in red. And we just need to look at lysine's side chain pKa, which is 10.79. So let me just highlight this, and its pKa is 10.79. And finally, let's look at glutamic acid. So I'll underline this in orange. And then on the chart, it's found here under acidic amino acids. So for its side chain, it has a pKa of 4.25. And for its alpha carboxy group, its pKa value is 2.19. So this is the hydrogen on here. Its pKa is 2.19. Okay, so now we know all the pKa's of all of these different structures, and we can finally try to answer our question. So the first part is to draw the structure as it would appear if placed in a solution whose pH is 1. So that's a very low pH value. And I'll just write down here that when your pH is less than your pKa value, then this tells us that the groups are protonated. So every time we have our alcohol groups, that just means that they'll have their hydrogen on. And when we have our amine groups, that means that they'll have an extra hydrogen bonded to the group. So now let's try to draw out what this chain would look like. So notice that all of these pKa values are greater than the pH equal to 1. So they're all going to be protonated. So the amine group on our tyrosine will have an extra hydrogen. So this will be protonated. And then I'm just going to draw the rest of my chain. So bear with me because it's a long chain. And in the case of our alcohol group, this just means that it has the hydrogen on. So I'm not going to add an extra hydrogen onto there. And then we'll just continue on with the rest of our chain. So glycine was the easiest one. It just has the hydrogen there. And then on to the next amino acid. It's going to draw this as a line structure to make it easier. And now this amino group is protonated. One, two, three. And then finally, our end group. Okay, so this is the structure when the pH is 1. So notice that our amine groups are protonated because their pKa values are greater than the pH. Okay, so now let's do the second part of our question. Show the structure and calculate its net charge at pH 12. So I'm going to start a new page. Obviously, I don't think I can fit everything there. So this is for 6b. And the pKa, or the pH, is now greater than our pKa values. So when the pH is greater than your pKa, this means that the groups are deprotonated. So now let's draw our amino acid chain. So we have our amine group, and then we have our tyrosine. And if we look at the alcohol group on our tyrosine, then it becomes deprotonated because now the pH is 12. And then let's carry on writing the rest of these. Again, our glycine just stays the same. And then moving on, we have our lysine. And it no longer has an extra hydrogen. And then finally, we'll have our glutamic acid. And its carboxylic acid group is now deprotonated. And the same thing with its alpha carboxy group, it's also deprotonated. So now let's look at all of the charges in this molecule. We have 1, 2, 3 negative charges. So therefore, the net charge is -3. Okay, so now let's read 6c. Define the isoelectric point of an amino acid. State its importance in protein chemistry. Okay, so the isoelectric point, Let me write it down. This is when the charge of your amino acid or amino acid chain is neutral. So this is important in protein chemistry because it affects the reactivity and also the stability of a protein. Okay, so that was all of question 6. So let's see what the junior tutor said. The charge of the terminal amino and carboxylic groups and the R groups of the amino acids involved in the polypeptide varies depending on the pH of the solution. If the pH of the solution is less than the pKa of the group, that certain group will exist in its protonated form. Meanwhile, if the pH of the solution is greater than the pKa of the group, that certain group will exist as its basic form. Yep. So since the charge of the groups will vary, the net charge of the polypeptide also changes depending on the pH of the solution. And to compute the net charge, just add all the charges of the groups that can be protonated and deprotonated. So they show that the net charge is equal to the sum of the charge of all the groups. So here they have, in the case of tyrosine, glycine, lysine, and glutamic acid polypeptide chain, the structure of the polypeptide, including the pKa of the groups, is shown below. Okay, so it's slightly different values, but it is around the same, so 9, 10, 4, and like 2. I noticed they didn't include the one for the OH group on tyrosine, but I'll just keep that in mind down here. So now for part A is to draw the structure of the polypeptide as it would appear if placed in a solution whose pH is 1. So comparing the pH and pKa values, all the pKa are greater than the pH of the solution, therefore all of the encircled groups will be protonated. Okay, they circled all the groups. Yep, so that's correct. And then show the structure and calculate its net charge at pH 12. So pH 12 is greater than all the pKa of the encircled groups, therefore they will exist in the solution as their deprotonated or basic form. So I think everything's correct except they just forgot to include the pKa of tyrosine's side group, which is around 10, so this would also be deprotonated like I have here. And they calculated the net charge equal to -2, but it should be -3. So I'm just going to write that at the end. And then for part C, it says to define the isoelectric point of an amino acid, state its importance in protein chemistry. So the isoelectric point of an amino acid is the pH at which the charge of the amino acid is neutral. It is very important in protein chemistry since the reactivity and stability of the protein depends on its charge. Aside from that, the structure of the protein can be disrupted depending on the pH on which it is placed. Okay, so this solution, or this, I'll say explanation, and the structures are mostly correct. However, the pKa of the OH group on tyrosine, I believe. Yep. On tyrosine, around 10.07. So therefore, it will also be deprotonated when the pH of the solution is 12. This makes the net charge in part B equal to -3. But they had a really good explanation. I think they just forgot to write down the pKa of tyrosine. Yeah, so it has 10.07. Okay, so maybe they can fix that. So this solution, I'll say, is incorrect, even though it was mainly correct. Okay, so question number 7 is, how do you calculate the molar mass of hafnium-2 oxide HFI2? This is 1 hafnium and 2 iodines. Okay, so hafnium isn't a commonly used element, so that's pretty interesting that they would include it in this question. But finding its molar mass is still fairly simple. All you need to do is sum up the molar mass of hafnium and 2 times the molar mass of iodine. So these values can just be found on your periodic table. So the molar mass of hafnium is 178.49 grams per mole, and the molar mass of iodine is 126.90 grams per mole. So now if we add these values up, we get a total molar mass of 432.29 grams per mole. Okay, so now let's see what the junior tutor said. The molar mass of a compound is equal to the sum of all the atomic masses of the atoms involved in the compound. So they have mm as molar mass, but it can also just be denoted as a capital M, and it's equal to the sum of the elements Na, where N is the number of atoms, and A is the atomic mass. In the case of hafnium-2 iodide, the formula becomes this. And according to the formula of the compound, hafnium-2 iodide has 1 hafnium ion and 2 iodide ions, and from the periodic table, the atomic mass of hafnium and iodide is 178.49 grams per mole and 126.904 grams per mole, respectively. Okay, so for solving the molar mass, they added the values up and multiplied the iodine molar mass by 2, and also got 432.298 grams per mole. Yep. So this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And And also, if you enjoyed today's video, you can give it a like and a comment, and share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.